Greetings and welcome, friends. Welcome to our new zone, this yellow zone, orangish, yellow, sure. We're talking about exploring rational expressions. Rational, hopefully you guys are familiar with the mathematical concept of rational. Rational numbers are fractional numbers, am I right? Rational, think of the word ratio here, kind of a little root word there, right? Dividing two things, ratio, here's the word ratio there, right again, bam. So that's what we're going to be talking about, and we're actually jumping today into the idea of graphing rational functions. What happens if I graph these things? And notice I've already got a nice little definition here for you. A rational function is a ratio of two polynomials. All right, so let me give you like a couple examples of them. All right, so that would be like y equals 1 over x. That would be like y equals, or maybe I'll even use f of x. How about that? Ooh, looks more like a function that way. I could have like x squared minus 1 over x squared plus 2x plus 1. Ooh, fancy. That would not, however, be something like this. If I had y equals 2/3 x squared plus 1/5. That is not a rational function. So this one is like a no-go. And the reason this one's a no-go is because, yeah, sure, it has rational coefficients, but it's not a rational function. It's actually just a plain old quadratic function in this case. So be aware of that. Rational functions are actually dividing two polynomials. In this case, I have a constant and a linear being divided. Here I have a quadratic binomial divided by a quadratic trinomial, right? So that's what I'm referring to when I say rational functions, right? Think rational, ratio, fractional, maybe, something like that. So let's actually jump into a problem where I want to do the following. Let's see. Here we are. We're going to graph the following. What if I want to graph y equals 1 over x? And I'm going to talk about a lot of its features because these graphs are going to be different than any ones you've ever seen before. Yes. Gasp is right. So let's actually, let me show you what's going on with this first. We're going to gain a skill set and kind of talk about the general features and vocabulary, and then we'll actually graph for real some of these other ones, which will be nice. What? Gasp!
Wow.
Shockingness! Wow. All right, so this is what our graph looks like. It's kind of an interesting little thing. Good stuff going on here. And it's got some interesting features. Now, if I asked you about its end behavior, actually that's a whole can of worms. It's kind of tough to talk about. But, well, what if I asked you about the domain? Maybe we could start with the domain. Now, it appears as though this goes all the way to negative infinity, which it does, and all the way to positive infinity, which is fine. But it turns out it actually doesn't exist at a very particular spot. It actually doesn't exist at the line or at the point 0 when I plug in 0 for x. All right? It can never equal 0. Well, actually in two ways. X can never equal 0, but it also turns out that y can never equal 0 in a moment when I talk.
Like impossible.
Why?
That number, well, if it goes on infinite, it's like already going close to 1.
Yep.
Those numbers must be like infinitely small. Yeah.
Infinitesimal, even. Yes. It turns out that, yeah, it doesn't exist at those points. So my domain, I could say, is the set of all x such that x is not equal to 0. I'm going to get better with my little curly braces in a moment, I hope. My range for this, it includes everything except 0. So it's the set of all y such that y cannot equal 0. And it's easier to understand this vertical one, I think. What happens if I did plug in 0 for x? What if I did plug in 0 there? What's the problem? You can't divide by 0, right? So these holes in my graph, if I want to use that term loosely, occur whenever I divide by 0. All right, so if I'm looking for the domain, I specifically am interested, in this case, whenever a denominator of a fraction is equal to 0. Okay, that's what I'm kind of interested in. And now for the range, that actually is going to take a bit more of analysis. But before we go any further, these red lines, they actually have a name. The red lines, let's see, how could I guess I'll do this. They are referred to as A, S, Y, M, P. Yeah, like if I was playing Scrabble and I had these letters, you wouldn't think I'd be able to arrange them this way. T, O, T, E, S. That is the plural of the word asymptote. Asymptote, right? And what an asymptote is, all right, it's whenever your graph approaches a line but never gets there. All right, it's like your graph is like, man, I want to go hang out with the x-axis, and it's getting closer and closer and closer to it, and it spends forever trying to get close to the x-axis but never reaches it. It's like it's permanently stuck in the friend zone. It's like, aw, man, that's too bad. Aw, man, poor graph. Another way I could describe this, although this is not true for this instance, imagine if I told you, good news, everyone, you can leave class early today. However, you can only cut your distance to the doorway in half every minute. And so like 1 minute goes by and maybe you were 16 feet away and now you're 8 feet away. And you're like, oh boy, this is good. And then another minute goes by and now you're 4 feet. And then 2 feet. And then 1 foot. And then half a foot. And then a quarter of a foot. An eighth. A 16th. A 32nd. A 64th. A 1/128th. A 1/256th. A 1/512th. A 1/1024th, right? A 1/2048th of a foot, right? And you're just like cutting in half and in half and in half. And in theory, all right, mathematically, you would never get there. Now, within the constraints of our actual universe and perhaps your muscular dexterity, you wouldn't be able to split atoms with your feet, like moving closer and closer to the door and then splitting quarks, etc., right? But the idea is that you would never reach the door, right? That's sad. However, we could all agree that you were approaching the door, right? I think we'd agree, right? That's the direction you're heading, but you never ever get there. So yeah, these are getting infinitely close, but never reaching it. All right. Actually, lame little side joke right here about asymptotes. Imagine like you were out in California and you went to like Comic-Con convention, right? And you got like a whole bunch of swag. You know, Hank, stuff we all get. And let's say like to carry your swag, you got like these awesome like gift bags to carry them in, but they're like really like the big shoulder strap kind. And so as you're leaving the convention, at the same time the surfer dude, he happens to be coming up out of the water with his surfboard, and he sees you with all your awesome like superhero bags and masks and signed memorabilia and whatnot, and he sees you carrying your 2 gift bags that are giant, right? And he just says, and you know what he says? He says, awesome totes, bro. Huh? Awesome totes. Because you have tote bags.
That's like the worst joke.
That's the best joke in the world. That's amazing. But
this is why this video is 55 minutes long.
this is why this video is so long. Exactly. So if I want to describe where these asymptotes occur, asymptotes, this vertical one occurs when x equals 0, and this horizontal one occurs when y equals 0. All right. Now, in addition to this graph, I'm giving you another tool to analyze this, in which I would have a table of values. Okay? And actually, before I get there, I want to talk about end behavior again real briefly. What is the y value approaching as x goes to infinity?
0.
Y is approaching 0. All right, because y is not going up towards infinity as well. Y is also not going down towards negative infinity. All right, I'm slowly deleting this. Y is actually getting closer and closer to 0, but never getting there. So if I was to describe the end behavior here, I would say y is approaching 0 as x approaches infinity. All right, similarly for this side, y is approaching 0, this time from the negative side, as x approaches negative infinity. All right, craziness. I know. So let's take a look at this. Here's a little spreadsheet I've made up, and I'm going to actually share this with you as a Google Doc, in which what we will do is, check this out. This might require a little bit of math here for us. I've automatically created a table of values here, where I plug in some really big negative numbers and really big positive numbers, right? And all you do is you define your function y. All right, so I'm going to hit equals, and our function is 1 over x. So I'm going to do 1 divided by, and what is x in this case? Well, x is this negative 1,000. So I'm going to either click over here or tell it to hit, A3 is what I could type in. And I hit enter, and what that does is it gives me the equation for, right, the y value, the output when x is negative 1,000. And then what I could do is, now notice when I drag my mouse over to the right, it becomes this little plus sign if I get it right in the corner. And what I'm going to do is I'm going to get that, click on it, and drag it down. What it's doing is copying my function or formula down, and when I release here, it's redefined this whole thing, all right? So it's giving me the y values for that, right, input and output. Now, it's got this additional feature, C, where that's just the center that it's focused on. So for instance, if I wanted to focus on -5, notice -5 is now the middle number, and it's analyzing around there. In this case, I do want 0 to be the center that it's analyzing. So let me copy this table here for us, and we'll talk about this. Talk about it. Paste. Here we are. Paste. Yeah, I'll do it right there. So if we analyze this, notice what this shows us, okay? Regarding the domain, what does this mean? Right, someone earlier said hashtag div/0! Which I don't know if Twitter allows you to use symbols such as slash. I imagine exclamation point mark, whatever, is probably acceptable.
No.
But you can't have an exclamation point mark point. No, really?
It just cuts it off.
You can't be excited about anything on Twitter? That's too bad.
Hashtag excited.
Can I write hashtag exclamation point with the words exclamation point?
Hashtag this video is going to be so long because we're not.
No, it's fine. It's fine. We're good. Actually, it's all computer programming based analysis right here. But anyways, yeah, this is basically saying you can't divide by 0. All right. Now it turns out if I was to zoom in and analyze specifically what was happening between -1 and 1, which I could, I would see some very interesting behaviors where when I approach 0 from the left, this is actually approaching negative infinity, which is crazy. Yeah, that goes all the way down to negative infinity. I don't know if you knew that, but that's craziness, isn't it? And the reason is, think about this. If I have 1 divided by 10, that's a small number, right? 1/10, it's like a dime, 0.1. If I do 1 divided by 1, what do I get? 1. 1 divided by 1 is 1, right? If I do 1 divided by 0.1, that's like asking the question, how many dimes go into a dollar? And you would say 10, right? Or if I ask what is 1 divided by 0.01, that's actually going to be 100, right? Or 0.00001, that's going to equal 1, 0, 0, 0, 0, all those zeros, right? I think I miscounted, bam. So the point is, the smaller or the closer I get to 0, the bigger the outcome becomes. In this case, I was plugging in positive numbers, so I was technically simulating this, where I was approaching 0 from the right, and I was getting bigger and bigger numbers.
So,
If I, question, comment?
yeah. So to like get your first starting graph, you have to just do y, whatever y equals, you have to plug that in, that's what
I'm going to actually make this table available for you because it's smarter than just using your graphing calculator, which is kind of linear incremental on the x value. But yeah, I just want you to see this, and I'm going to teach you a bunch of tricks so you can shortcut find where your asymptotes exist, which is good news for us. But my point is, the smaller the number I plug in, the bigger the outcome becomes. Dividing by a very small number gives me a big number. And when I divide by a negative small number, then it gives me a negatively big number, if that's not an oxymoron, I don't know. So that's where those values come from, okay? And you can see that this was actually getting increasingly negative right there, is what was occurring. There we go. So that's what we had going on there. And if I approach 0 from the right side, you can see that tiny numbers getting bigger. And if I plugged in something smaller than 1, bigger than 0, it's actually going all the way to positive infinity, which is interesting. I think so, anyway. So yeah, from this side, it's approaching negative infinity. From this side, it's approaching positive infinity. And what's happening as x goes crazy negative? What's happening to y? It's getting smaller. It's getting closer to 0, and specifically, it's approaching 0 from the negative side. I might actually put a little minus like as an exponent almost. So I'm approaching 0 from underneath, you could argue. And what's going on here? Right, that's getting smaller and smaller, and that's approaching 0 from above, from the positive side. So I want to point out that this describes where my vertical asymptote occurs, and this is describing my horizontal asymptote. Okay, the fact that it's approaching a number, it's not approaching infinity, right? It was approaching 0 in this case. And we won't see all of our graphs approaching 0 for the horizontal asymptote. They can actually approach different values, and that's where I want to show you some different exemples to equip you with that. So what you're going to do is you're going to analyze to figure out the domain, the range. That's going to take a few tricks. Figure out where the asymptotes are. You'd have a nice little table, and then hopefully we'll have enough information to draw our own graph. So let's look at another problem real quick. Example. Let's say I want to graph the following. What if I want to graph y equals 1 over x plus 2? All right. And 1 over x plus 2, if I want to figure out the domain, for the domain I'm specifically interested in when is the denominator equal to 0? Because I don't want it to equal 0. So I could actually do some scratch work. I could say x plus 2, I don't want you to equal 0. And then if I solve that, I'll realize I get x cannot equal negative 2, as our friend just said. So the domain is the set of all x such that x cannot equal negative 2. All right? Now for the range, that takes further analysis. We'll end up doing our table. But we can describe our asymptotes. ASY, I'll just abbreviate it. Where this is likely going to be also a vertical asymptote for us. Technically, I can't guarantee that until I have the table, but in this case, it'll work out that way. So let's make our table for this. So I'm going to skip on over to Excel, and I'm going to write my equation. So I'm going to edit this cell. Instead of 1 over x, this time it's 1 over x plus 2. If I do this, what's wrong with this formula compared to what my function's supposed to be? It's a matter of order of operations. 1 over x plus 2 is different than 1 over x plus 2. All right, all in parentheses. All right, so I have to make sure I have that correct. So let's select this, and we will drag it down. Drag on. And we can see some results. Excellent, excellent results. Let's see. Yeah, go away. Go away, man. Let's see. Actually, I might even realize that my div 2 is at negative 2, so I might enter that and have it center at that location. So once I have the table of values, what you could create this table by hand if you wanted, or maybe with a calculator as well. Let's analyze this. Now, is this in fact an asymptote? Well, what's it approaching as x gets closer to -2 from the left, from the negative side? What's this approaching? It's getting, well, 0.25, 0.33, 0.51. It's actually approaching negative infinity. And I might actually maybe make a modification of this table where it analyzes values between this number and our center point. And from here to here, what's it approaching? 0.25, 0.33, 0.51. It's actually approaching positive infinity, right? So this appears to actually hold true that this is an asymptote here, so that's good news. Let's look at our y value. This is getting smaller and smaller. I think you'd agree. It's approaching 0, and what side is it approaching 0 from? Negative, and this is approaching 0 as well. It's getting smaller and smaller from the positive side, right? So my range likely is going to be the set of all y such that y cannot equal what? Does y, the y values, this chart, does this ever equal 0? No, it's just going to approach 0. All right? So what's going to happen? So our horizontal asymptote. What? No, I'm going to show you next example one where it doesn't quite do that. So if I was to graph this based off of this information, actually maybe I can even do this. Bam! I'm just going to steal this. Watch this. This is how cool I am. I'm a thief, yo. Robin Hood, stealing your grids. Here we are. Paste, not P2V. So if I wanted to draw my own graph of this, based off of the information I'd gathered, this is what I would do. I would draw my vertical asymptote at x equals -2. That was terrible. Ding, 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 ding. And my horizontal asymptote at y equals 0. Ding, 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 ding. Right? And now I just got to figure out, where does this graph exist? Well, it looks like it's negative to the left. Right? It was approaching 0 over here, right? It's approaching 0, so it's getting closer and closer to that. Something like that. It's approaching negative infinity here. So I'm guessing it probably has this behavior in between there, something like that. At the far right, it's approaching 0. And it's hard to actually try to draw that accurately. And as it approaches -2 from the right, it was approaching positive infinity, I believe, right? Yeah, and that's what we had verified there as well. So you can see that the graph probably looks something like this. Yeah. Something to that effect. So let's actually graph that using tecnología. 1 divided by parentheses, you're not going to fool me, x plus 2. And what do you know? General idea, I was pretty good. Technically, I could have pulled like my y-intercept if I wanted, being 0.5 up here, and that would have helped me narrow down my search a little bit. But I've got the right asymptotes, I've got the same general behavior. I'm happy with that. I'm overall, generally happy with that. Now let me show you some tricks for horizontal asymptotes. Horizontal asymptotes. Whoa. Now, let me actually show you a few different things. We're going to keep modifying this graph. Now, horizontal asymptote occurs at 0, right? Right? Agreed? Let's just make this 1 over x again, right there. Actually, maybe I'll make this a medium thickness line. So let's say, what if I have x over x? Well, that's not actually that interesting, because x over x, what's that equal to? 1, although question about the domain of this graph. What is the domain? The possible inputs. It looks like it goes from negative infinity to infinity, right? However, the denominator can never equal 0, right? But if the denominator is 0, so is the numerator. What's 0 divided by 0? In this graph, it says it's 1. You might say 0 divided by anything is 0. You might say dividing by 0 is undefined. Turns out it's actually undefined in this case. Calculus will be able to bring some light to those questions later. To make that a little bit more interesting, let me make this guy. Now, what do we notice about the horizontal asymptote? Where is the horizontal asymptote? It's occurring at y equals 1, right? That's true, that's true. And it's not related to this one. Notice if I change this to a 3, the horizontal asymptote's actually still in the same spot. It turns out the horizontal asymptote, if the degree of your leading coefficients in numerator denominator are a tie, so for instance this is a first degree, that's a first degree, then your horizontal asymptote is just going to be the ratio of their leading coefficients, so 1 over 1. So to verify that, notice if I change this to a 2x over x plus 3, now my horizontal asymptote is at 2. All right. Now, to explain this in general, think about really big values of x. All right, really big values of x. If I'm comparing x to x plus 3, imagine you show up at a party and you're like, hey man, I'm a billionaire. And someone else is like, oh yeah, I have $1,003,003,000. Like, you just be like, so what? Like $3? I'm still a billionaire. Like, cut it out, man. Don't be a jerk. Besides, you're gonna tip the valet $3 on your way out of this party, and then we'll be even again. And that's essentially what's happening for really big values of this, right? A billion compared to $1,003,000,000 is 1-ish. It's kind of like 1, right? A gazillion divided by a gazillion and 3. Those are even closer. It's kind of like 1. And that's what's going on here, all right? So when it's a tie between those leading coefficients, it's just the 1 over 1 that's going on. So if I have this as if I'm comparing a 2 billionaire compared to a $1,003,000,000 heir, that's just dividing those two things. He kind of has roughly twice as much money, all right? And that's what we see occurring, and especially for these super extreme values of x, that is what's going on. Now, what happened whenever it was the other way around? What if the greater degree was in the denominator? It appeared that the horizontal asymptote was at y equals 0. Well, what if this is the case? What if it's x over x squared? Notice it's actually still at 0. That's actually a really interesting graph right there, isn't it?
No.
Now, in this case, this does exist at 0, which is weird. But you would still potentially describe this as having a horizontal asymptote. The reason is because the horizontal asymptote is all about being defined by the end behavior, so it is still approaching 0 at those extreme values. What if the numerator has the larger exponent? Now think about this. Which of these is going to grow faster when x's get bigger? X squared, right? Comparing a parabola to a line x plus 3, the steepness of a parabola, the parabola is approaching infinity faster. Now, for really big values of x, both of these are approaching infinity, right? Big number squared compared to big number plus 3. The bigger those numbers get, both of them are approaching infinity, but the x squared is approaching faster. And what we have here, this is actually really bizarre. This actually is asymptotic, but it's a diagonal asymptote. Craziness. You don't have to worry about any of that for the math class we're in right now, so fortunately we're good. But as far as the end behavior goes, what is this approaching as x approaches infinity? The y value is just getting bigger and bigger. How do I describe that? Y is approaching infinity, right? So that was kind of our three-part analysis, and I'm going to try to summarize that here. So if, for horizontal asymptotes, all right, it's all about the ratio of the leading terms, or comparing the leading terms' degrees. Okay? If my numerator, if I have x squared over x, then that means y is approaching infinity. All right, there's no asymptote. If I have the denominator with a bigger exponent, then that means y is approaching 0. And if it's a tie, so let's say x to the second over x to the second in this case, I'll add one more component here. What if this is ax squared over bx squared? Then y is actually just going to approach a over b. All right, so that's my summary of horizontal asymptotes, as summarized as I can make it. All right, so we graphically observed that taking place. So if I want to figure out horizontal asymptotes, it's all about that. Now, technically, we did see that one graph where it was kind of like this, and it was asymptotic at the ends, but its range still included that value. Be aware of that. That's something that we'll have to, just keep our eyes out for. But the idea is that it's all about comparing those leading terms. Because when it comes to really, really big numbers, the leading terms are going to be the ones that have the most influence on the shape and behavior of our graph. Let's see, one last example. Last example. Here we are. Let's say I want to graph f of x equals x over x squared minus 1. So let's analyze this. So I want to figure out the domain, the range, and the asymptotes before I can graph this. Now, for the range, since I was just talking about comparing the leading terms, when I compare these leading terms, which has the larger degree, numerator or denominator? Denominator. So according to our previous rules that I just told you, what is my horizontal asymptote going to be? It's in our notes, we just wrote it down. Y approaches 0. All right, so my horizontal asymptote is going to be y equals 0. All right, there's a horizontal asymptote. Likely there's also going to be a range restriction in that case, but we'll get to that in a minute. Now for the domain, how do I analyze domain? I'm always interested in when is my denominator equal to 0. So when is x squared minus 1 equal to 0? Well, one of the things I want to point out, it's sometimes actually worth factoring these. X minus 1 times x plus 1, you might have realized that was a difference of squares there. So my domain is going to be the set of all x such that x cannot equal, and x can't equal two things. What two things can't it equal? 1 or negative 1. If this is 1, 1 minus 1 is 0. 0 times whatever this is 0. And if x is negative 1, negative 1 plus 1 is 0, and 0 times whatever this is 0. Right? So x cannot equal negative 1 or 1. And it's likely going to have two vertical asymptotes. All right, so 3 asymptotes all together. So let's actually throw this in the Excel. So let's program our function here. So this time it's x over x squared minus 1. So x for me is the cell A3, that's my x value. And I'm dividing by parentheses A3 to the second, that's squared, minus 1. All right? So I've programmed that in carefully, taking note of order of operations, PEMDAS in it, right? Bam. So let's drag this down by the corner when I get the black plus sign. Bam. There we are. And aha, behold, friends, behold. Let's take a snapshot of this and analyze it. So if you didn't have technology to assist you on this, you could do this all making your own table of values by hand sort of thing, but it wouldn't be a lot of fun. So let's see if we were right about our horizontal asymptote. What is y approaching as x gets really negative? Smaller, smaller. It's approaching 0, and specifically from the negative side. Okay, and now I've got two vertical asymptotes, or two portions where I'm undefined. And notice they do happen to occur at both of those locations. So I am getting the correct values for my domain. Now, as far as approaching this first one, it's negative 0.26, negative 0.375, negative 0.66. Those are getting bigger. I believe this is actually approaching negative infinity. Now, in between these, we'll have to analyze this. But notice this actually. I was about to say that my range was going to not have y ever equal to 0. But there it is, y is equal to 0. All right, so this is one of those situations where it will cross the x-axis there, but the end behavior will still be asymptotic. That's right, I just used the word asymptotic, all right, to describe this graph. That's an appropriate, accurate word. Approaching this second vertical asymptote from this side, it's getting bigger and bigger. That's approaching positive infinity. And approaching large numbers, y is approaching 0 from the positive side. All right, so if I wanted to graph this, let me delete this guy, take a snapshot, and I'll show you what I can, and we'll see how close we can get. So the first thing we should do, oh, actually, I didn't define my range yet. Oh, range is the set of all y. It's just everything seems to work because 0 even worked. 0 would have been the one I would have said wouldn't work, but it did. It did. So let's graph our asymptotes. So I have one occurring at -1 vertically, and one occurring at +1. Oh, that was so, man, not a straight line there. And then horizontally, I'm arguing that there's one at y equals 0. And let's see if I can get the location of this graph correct. Here it's all under the x-axis. It's all negative here, so it's actually doing this sort of thing. And here it's all positive, so it's doing this sort of thing. And I could actually take some y values if I really was interested to get roughly where that exists. And now I know that it's equal to 0 here, but now my question is, does it do this, where maybe it's asymptotic like that? Does it do this, where maybe it bounces off the graph, which is possible? Does it do this? All right, or does it do this? And so there's actually 4 possibilities. The only way to figure that out is to plug in values on both sides and find out where they are. All right, so I'd have to plug in a small negative number between -1 and 0, plug in a small positive number between +1 and 0. In this case, I think I can just cheat on my spreadsheet. I'm going to plug in -0.5 and -1 there, and +0.5 and +1 there. So we can see that to the left of 0 we're positive, and to the right of 0 we're negative. So I am going to assume to the left of 0 we're positive, so it must be asymptotic this way, and to the right of 0 we're negative, so it's looking like that. So let's see if we can actually get this graph for real. Oh, what was our equation? It was x divided by x squared minus 1. And behold, I believe we're right. Okay? So crazy stuff going on with these. The majority of our efforts are all about the asymptotes. It's about the end behavior. It's about being able to kind of analyze what's going on around those asymptotes. And yeah, so we end up getting these interesting graphs and relationships as a result. Kind of cool stuff going on. Sometimes you have to be careful with your domain or range sometimes. Well, actually, domain you can be more confident about. Range, we might have to analyze what's going on in the rest of the graph to see what's occurring. Let's see. I think that we're good. Oh, that's one of the last things I wanted to point out. You don't have to write this example down. But suppose I have this equation. What if in my numerator I have x plus 1? Well, actually, let me write it out this way, just so it's more interesting. What if I have x squared plus 4x plus 4? That is, actually, if I graph that alone, that's a factorable polynomial, all right? With x plus 2 as one of its factors. Actually, x plus 2 is both of its factors. And what if I divide that by x plus 2, which I just said was one of its factors? So, Hank, x plus 2 is one of the factors of this, all right? This numerator could factor to be x plus 2 times x plus 2, and I'm dividing by an x plus 2. So in a sense, I could cancel out 2 of those x plus 2's, and I'd be left with just 1 in the numerator, which graphically speaking would look like a line, which is the line y equals x plus 2. Now, this looks like a regular old line, but if I was to mathematically have this accurately represented, it actually would have a hole in the graph when x is negative 2. Because I know that according to the domain, the denominator can never equal 0. It's never going to work out. And that's actually what's going on there. So this is an interesting case. We'll analyze this later on, where if you can factor one of your things and cancel it out, you might have a graph that looks normal, but has a hole somewhere occurring wherever the domain doesn't exist. All right? So thanks for watching, Internet friends. Tienen un día el más bien del mundo. Bye-bye. Cray, cray.